Does it work? Cool. Okay. Thanks a lot for the introduction. So today we're going to talk about, we see how our plan as a Ethereum community to try to migrate Ethereum to post-quantum cryptography. We see what actually means. A little notation that I use always. Assuming you get something to eat and you're tired, you want to get a nap, do it. But when you see the red stars, it's a good time to wake up. So for people that don't know Ethereum, I have here like a macro view of how Ethereum actually works. And we have 4 macro areas. So we can, in a long, if you zoom out, we can see Ethereum being in 4 different parts. The execution parts, that's basically like what we see, like when we use Ethereum, we use get or nevermind or whatever. So it's like where the transaction happens. Then we have the consensus part where the magic happens. And yeah, where the validation of the blocks happens. Then we have this new part of Ethereum that is called data availability sampling, or DAS, or 4844, or proto-dunk sharding, you call it whatever you want. And you have this part that is for the future, for light clients, that is called stateless Ethereum. And they're like, we have these vertical trees. Behind data availability sampling, I forgot to mention, there are all these things called rollups, or L2. And you can see there are Optimism, Arbitrum, Linea, whatever is your test. Now, if we want to put a bit of, to see inside the engine of this area of Ethereum, we have this 4 part that is cryptography. So what is the cryptography behind any of these components? So behind the execution layer, there is something called ECDSA signatures. That is the same one that uses Bitcoin, by the way. Behind the consensus, we have another really nice piece of math that's called BLS signature. And behind the data availability sampling, we have something called KZG commitment. You don't need to know what it means, just put some names here. We'll see shortly why they're all here. And behind stateless Ethereum, there's something called Pedersen commitment. Now, one thing that is in common behind all these 4 things is one thing, that is elliptic curve. So whatever is in the engine of these 4 components is really elliptic curves. And yeah, it turns to be a problem in the long run. Again, which kind of elliptic curves are behind these technologies? Behind ECDSA, we have one elliptic curve called SecP 256K1, and again, it's the same that Bitcoin uses. And behind BLS 12, behind the consensus and data availability sampling, we have another pairing-friendly curves. No worries if you don't know what it means, but it's called BLS 12381. And behind stateless Ethereum, there's another curve that it turns I kind of made with another collaborator. It's called Bandersnatch. Well, yeah, it will not last long, unfortunately. It was actually ready to be shipped, but given the fact that we have this quantum menace, it probably is not going to happen. Before to see why, I swear I have only 2 slides that shows a little bit of math. But just to give there's no really math behind it, just like an idea. And we'll see why we cannot use any more elliptic curves at least. So these are elliptic curves. And basically, a rough idea of how it works, this comes from some guy in the old Greece called Diophantus that discovered this really nice idea that if you have 2 rational points, then no worries what it means, if you know what it means rational, in elliptic curves, you can always find a third one, and the way to do it is just trace a line between the 2 points. This line hits the curve in the 3rd point, and you have these weird additions that is defined like this. What actually we use for cryptography is not even addition, but is a kind of scalar multiplication. What you need to remember about this talk is only one little thing. This problem. This is a really simplified one, and it's called, so the problem is not simple, but I simplified it here highly, and it's called DLP, or discrete logarithm problem. And more or less, what happens even now when you connect to the internet, or when you use Ethereum or Bitcoin, there are some exchange of points, especially in the internet. Your browsers, let's say Chrome or Firefox, will send some points to the server. And the discrete logarithm problem is basically having this these 2 points that you know they are public, and you need to know a kind of scalar that, let's say, connects these 2 points at high level, we'll say has a relationship between 2 points. And so far this worked. This concept was invented for elliptic curves in around 1983, 84, and it served us well for many, many years. But yeah, I have a bad news. This is not going to last long, because in 1994, we got one guy, one researcher called Shor, that invented the so-called Shor algorithm. This will basically destroy completely our internet and what we know about Bitcoin or Ethereum, of any other public key cryptography that lies around. And so we need to do something. Not doing anything is not an option. One thing, just to warn you, is like, don't worry. For now, at least. Even for the future, actually. Vitalik wrote a post some years ago, and it's very nice. You can read this, it research, and basically tells what to do in case of emergency of a quantum computer. And yeah, but in a nutshell, what he says is what I told you before, that quantum computers breaks public key cryptography, but it doesn't break private symmetric cryptography. So hashing, for example, is not broken. It's broken, but not in a so bad way. It's just like the algorithm efficiency is only quadratic, so just double the key and you're kind of fine. And the reason why I'm telling this is if you have a public key, an address in Ethereum, it is the hashing of the point of the elliptic curve. What you need to remember is not this, but you need to remember is that if you have an Ethereum address where you have some ether and you never move any ether from that address, you're safe even with a quantum computer. So if you see a quantum computer coming, just move your ether to a fresh address and you're fine, because they catch a part on this slide. So this means hashing, this means SHA-3, this means symmetric cryptography is not broken by quantum computer. But at the time you're actually doing one single transaction, well, goodbye your ether in case there is an attacker with a quantum computer. So we need to find a replacement, and as we said, elliptic curves doesn't work anymore in the future. We need to find some replacement. We have kind of 4 or 5 micro areas. The first one I already mentioned, hash-based cryptography, will probably resist it. Then we have so-called lattice-based cryptography. I'm not telling you what it is in details, just put here some sentence, but really no need to remember. We have some other area called code-based cryptography. It's really, really old. It's actually older potentially than the invention of elliptic curves, but is now coming back to be modern again, because a broken clock is always right twice a day. Then we have multivariate cryptography, and then, of course, my favorite part, I see some people here that do this kind of research, there's super singular elliptic curve isogeny cryptography that is awesome. Now, the bad news is that when you kind of try to replace the stuff, it takes time. So it's not immediate. So we need to act in time. So as I said, also the internet cryptography is going to be broken by quantum computer. Indeed, the NIST, that is like one kind of American association, let's say, that is behind the cryptography of the United States, announced a kind of call for proposal for post-quantum cryptography already in 2016. And already in 2017, people start to propose new cryptography based on the assumption we've seen in the previous slides. So there were some assumptions based on lattice, some on code, some on multivariate. And what happens in this kind of situation is like danger game, or like, I don't know, people try to kill each other. Namely, like cryptographers try to kill others' proposal until one wins. Or in this case, there's not only a single winner, but yeah, the idea is to have like few kind of proposal that will replace the elliptic curve cryptography that we deploy now. Well, this continues. So in 2018-19, it was the first round of evaluation. So it means that some of the candidates were quickly eliminated. Actually, I think 4 or 5 were already eliminated the nights of the proposal submission by a few people. Few years after, we got some other selection, so other standards or other algorithms were killed. And finally, in 2022, we got a selection candidate for the standardization. And yeah, well, the implementation started, continued to be there. And yeah, as you see, like, in order to have something deployed by 2030, or I think the maximum for United States government software 2034, well, they already started in 2016. This takes really a lot of time. Whoever writes software knows that is not easy. So you need to standardize in this case, plus writing the software, plus test. So also for us, it's going to take time. By the way, these are the four kind of winners. We have one winner for the key encapsulation, that means encryption, and it's based on lattice. And we have three winners for signatures. There are Dilithium, Falcon, that are, again, lattice, and Sphinx, that is hash-based. Now, we already started as a Ethereum Foundation or as a Ethereum community to work on some post-quantum algorithm many years ago. Already in 2020, I have here some papers that tells some stuff we've been doing. Not now, already like 3-4 years ago. Here we have an attempt of doing some multi-signature scheme from lattice. This is one of my proposals to use isogenies for single secret leader election. This again, the improvement of the first paper on lattice for multi-signatures. This again, me doing some isogenies for something called stealth addresses. So we were actually thinking about post-quantum for a while. Until 2024. 2024 was actually a topic here for quantum computer. The first things that caught the attention, not the media, but people that follows papers, was this paper on archive, and are from Google people, and they show some kind of breakthrough. One thing is like that we know, I'm not an expert on quantum computer, but basically at the moment, a lot of problems are not actually theoretical, but are engineering problem. And engineering problem tend to be solved with time, but tend to be solved. And here in 2024 was this paper from Google that they had some kind of engineering breakthrough going through in this paper, and it was still an academic paper. But people that follow Scott Aronson, that's one of the main people that do quantum computing, he kind of shifted his message. And when before was saying, yeah, start to replace your algorithm with something, it was kind of urging people to really start replacing their algorithm with something that's not RSA or elliptic curves. And then what actually moved a lot waters, and it's actually the same thing that happened in August, but it was for the mass. But basically, like the Google CEO was introducing this Willow, that is nothing else than a chip that does quantum computing, that is basically that paper of August 2024. But of course, like many people use Twitter and not many people follow Archive, but it's basically the same thing. Coming back to Ethereum, it's clear that doing nothing is not an option. So these are again our micro area, and we need to take time and try to study what we can do for a post-quantum Ethereum. Today we're going to only talk about the first part. So it's the part I've been working. People following Eth research might have seen some of my posts. And I've been proposing to use Falcon as an Ethereum transaction that will replace ECDSA. But people that follow the Ethereum, the Ethereum research knows about Beacon Chain, this big project announced by Justin Drake, one of my colleagues at Dev Connect in Bangkok. And that is going to tackle the consensus area. It's a really ambitious project which is going to last 4 or 5 years. And again, we have to find as well replacement for DAS and stateless Ethereum. As a result, probably Verkle tree, whoever here likes Verkle tree, it's probably not going to happen because, well, the paradox here is that at the moment, the way how we store data in Ethereum is called Patricia Merkle tree, that use hashes and is post-quantum. And if we go to Verkle tree, we'll use Pedersen commitment on elliptic curves there's not post-quantum, so it's kind of regressing. So probably what is going to happen is we skip vertical tree and we go directly to something called binary tree plus Poseidon. But again, in Ethereum, it's like the governance is, well, you know, it's not an easy thing, so we'll see what is going to happen. So, about replacing ECDSA. I've been trying to split the problem in three parts, and how can we replace ECDSA with a new algorithm? The first option is to do a hard fork. Doing a hard fork means do a new IP, doing a new release of Ethereum, and well, it's not easy. I mean, we are going, our item or release is about one release every 1.5 to 2 years, and it's a big thing. Clients need to write software, testing, and there are not many things that goes through. And yeah, but it's an option. How to do it? It's actually, technically, it's not really hard. I'm not a developer, so I can code, but not a great coder. I talk with the people of Get, and basically, the way to do it as doing Falcon as a EIP is basically like something really simple in terms of code. There's not many lines of code, and it will. These are only for people that follows the technicality of coding, but it's basically doing some new transaction type, and it's pretty easy. Indeed, if you're going to see, one of the pros of using a hard fork to do Falcon as replacement of ECDSA is that it's actually easy to code and fast, because it's going to be code that runs on the client software. The problem here is it's not future-proof. What happens is Falcon is broken. We need to do again a new hard fork, and you move again your ETH to an address that you can move and so on. Yeah. So is there any better way? And we have another possibility. There's something called account abstraction. This is unique for Ethereum. Namely, like if you think about Bitcoin has the same problem, it can do hard fork way. They can do a new algorithm replacing ECDSA with I don't know, Falcon as well, or whatever they choose. We all know that in Bitcoin things are really slow, but eventually they have to something. But they cannot do account abstraction, because account abstraction, I cannot introduce what it is, but it's basically a friendlier way to interact with Ethereum. And it's an option that only Ethereum has at the moment. And basically, like if you want to follow the account abstraction way, we have it right now. Account abstraction is reality. Whenever you log to Ethereum through a wallet that doesn't use a seed phrase, that use, I don't know, the passkey of your iPhone, Google account, and you're logging in Ethereum, you're actually under the hood using this awesome technology called ERC4337. And basically in Pectra, this is the next upgrade of Ethereum, you will have ERC4337 on steroids. It's going to be more in the protocol because it's in EIP rather than ERC, for people that knows what it means. And what actually are the advantage of the pros and cons? Because there are not only advantage of having an account abstraction solution. Well, it's really elegant and flexible. Namely, we can have more than one post-quantum signature easily. I just actually promised to some misogyny people that I will try to put sky sign, so it's on the roadmap. And so we can actually have more solution than not, because it's not hard-coded, it's really easy. There is some price to pay though. How things are at the moment, and you are writing account abstraction, it means that the validation part of the signature happens on chain. On chain means that you need to write solidity. Writing solidity means that it's not Rust or C or Golang. It's something really that you pay the price. How much is this price? Well, a lot. With the current contract of Falcon, not optimized, it's just like some contract at the moment on the internet, doing one Falcon verification, the easy part of Falcon, but it's the only one that needs to be on chain, is 25 million gas. That I don't know if you know it, but it's huge. Sphinx cost a bit less, but it's 12 millions. If you want to go to something even more exotic, like Mayo, it's, well, 938 millions. So, of course, this is not going to be an option as things are. We either optimize things at the contract level, and we have the possibility with some other improvement to the EVM, like EVM Max, for example, or we either start another solution that I call in my talk or in my post on It Research, the hybrid way. This is actually a good way to start. Hybrid way will actually means this. Will means using again account abstraction, but start to gentle, start to tackle rollups, start to tackle L2. In L2, for people, RIP doesn't mean that anything is dead here, it means something else. RIP is the correspective of EIP for rollups, and it turns out we already have one. So we have many proposed, but we have already one RIP proposed, and this is RIP 7212. And it's basically, if you ever used passkey to log into Ethereum, under the hood, use this. It uses this software that is deployed only on some L2. And in this case, we'll have the best of two worlds. So again, we have the good of account abstraction, so it's an elegant and flexible solution. It is easy to code and fast. And yeah, the problem here is that it's a start. It's temporary. It doesn't solve at all the L1 case, but at least it starts to cover the rollups. I'm starting to this. I start with the proof of concept. If someone is interested, you know how to reach me. I would like to end this talk with this actually things that was shared by Seth Lloyd in an interview in, when was it, in August. So when we'll have scalable quantum computer? He replied, I say 10 years plus or minus never. This is as well an option. And that's basically it.
Awesome, Antonio. Thank you so much. Time for questions. We have one up there. Yeah. Whoa. There you go.
Yeah. So my question is, so you kind of said that just hard forking is basically non-future proof because what if Falcon is broken? Have you ever thought about like using combiners for signature schemes?
Using combiner like
cryptographic combiners.
More than one, like it happens now with the hybrid.
Yeah.
For sure. Like that is an option. But you know, when you combine things, one of the most precious things you have for blockchain is space. That's why I've been proposed to use Falcon and not the lithium, because that's the space of the signature is shorter. That's why I would love to see isogenies, because the keys is even shorter.
Sure.
So this will be using combiner is good from the perspective of future proof, but in terms of space, it's not ideal. In terms of execution, so the thing that differs blockchain from other things, our laptop, for example, is that you pay for execution through gas and space through gas as well.
Yep.
So even one optimization you see on the cost of the transaction.
Yep.
But theoretically, it's a good idea.
Okay.
Thank you.
If it's okay. Thanks for the good talk, Antonio. You had the slide with the gas costs of verification. Do you have a number for what ECDSA would cost in terms of?
Sure. No, at the moment ECDSA is 2,000 something, nothing. Okay. And the reason why, because it's hard coded. I mean, this indeed our contract is written in Solidity. If we use the hard coded way, also Falcon will cost us less as ECDSA. So yeah, but it's like order of magnitude more.
Super. Thank you so much. Big round of applause for Antonio.